Hello, my name is Frederik Madsen, and I'm a PhD fellow at the IT University of Copenhagen. This is my presentation of the paper on the subject of non-equivocation, defining non-equivocation in synchronous agreement systems, which I have written together with Søren Debois, who's also from the IT University of Copenhagen. The central point of the paper is that we have noticed a discrepancy with the use of the term or the uses of the term non-equivocation in literature. These discrepancies leads us to two different notions of non-equivocation, which we formally define as fault models, after which we examine their properties with regard to synchronous agreement problems. One of the properties that we examine is that of fault tolerance bounds, where we found the following. So this is a table showing three different synchronous agreement problems under different fault models. The three different synchronous agreement problems are that of broadcast agreement, interactive consistency, and consensus. And the fault models are the Byzantine, the authenticated Byzantine, the omission, and the crash fault model, in addition to the ones that we define here, namely that of strong non-equivocation, which has a fault tolerance of n greater than t for broadcast agreement and interactive consistency, and n greater than 2t for consensus. Weak non-equivocation, on the other hand, has n greater than 2t fault tolerance for all three problems. This clearly indicates that the two notions are different. Another interesting point here is that weak non-equivocation is, to the best of our knowledge, the only fault model with these fault tolerance bounds for broadcast agreement and interactive consistency. So I'm now going to give you a few examples from literature with different uses of the notions of non-equivocation. We start in 2007 with Chun and co-authors who define the notion of equivocation as that of a faulty process lying in different ways to different processes. And by preventing this faulty behavior, they achieve an increased fault tolerance of the well-known algorithm practical business fault tolerance, or PBFT, from n greater than 3t to n greater than 2t. And they prevent the faulty processes from equivocating by a trusted cryptographic component that where a process stores and attests a single value per message that it's supposed to send, or per broadcast round, if you will. In 2009, Levin and co-authors improve or optimize this primitive. So instead of being an entire memory block, it becomes a trusted incrementer. And in 2012, Clement and co-authors shows that this notion of what we say is weak non-equivocation is not enough to achieve the fault tolerance gains, but that you also need transferable authentication if you are in an asynchronous system. All of these are or use a non-equivocation notion where the process are allowed to omit any and all messages if they want. On the other hand, we have that of on the other hand, in 2012, Jaffa and co-authors examined the fault tolerance gains achieved by non-equivocation, and they do that by applying partial broadcast channels in different configurations to achieve different fault tolerance bounds. And similarly, in 2016, Lee and co-authors used partial broadcast primitive to prevent equivocation. And in 2019, Khan and co-authors use a local broadcast model to prevent equivocation. These three notions, or this notion of non-equivocation does not allow the process to omit any message. It is there are certain messages that cannot be omitted if other messages have not been omitted as well. Yes. So non-equivocation refers to a limitation of the type of fault a process can commit. And so we want to define the two different notions here as fault models. And to do so, we need a system model. The system model we have chosen is relatively simple. It is a synchronous Brown-based model with reliable point-to-point channels. And we use the framework of Pierce, Shostak, and Lampert to represent all the messages that are sent in the system. In essence, each round, each process must broadcast the values they received last round and from whom. And then we store all these sent values and process sequences in a map called sigma. Let me show you an example. Given three different processes, P, Q, and R, we let P broadcast the value V in the first round. This is represented in sigma as the process sequence PQ mapping to V, which can be interpreted as P tells Q the value V, as well as the process sequence RP mapping to the value V. In round 2, each process then repeats what they received or broadcast what they received, which values they received last round and from whom. So in this case, R is going to broadcast the value V and that they received it from P, and Q is going to broadcast the value V and that they received it from P. In sigma, this is represented as the process sequence RQP mapping to the value V, which can be interpreted as Q telling R that P told Q the value V. Similarly, the process sequence QRP is going to map to V. In general, this can be interpreted as whenever you see a sigma where the process sequence W maps to some value, then W is the path that the value has traveled in the channel, or which channels the value has traveled. As long as none of the processes on that path are faulty, in which case, so if a process on that path is faulty, then there can occur omissions, or the faulty process can even lie about whom they received the value from, or which value they received. So this framework allows us to formally and precisely define the two different notions of non-equivocation as fault models. We start with the strong non-equivocation fault model. So strong non-equivocation must encompass the idea that equivocation is prevented by ensuring that every process receives exactly the same for each message sent. Or in other words, each round, a faulty process must atomically either send the same message to all other processes or send no message. So this allows a faulty process to still lie, and it fits with a broadcast channel where all recipients on the channel either receive the same message or no process receive any message. So as I said, the process is still allowed to lie, which is represented here as R sending the value U to P and Q, where it was supposed to send the value V. Furthermore, however, R is not allowed to omit any messages. So R could not send V to P and omit the message to Q, and nor could R send two different messages in a single broadcast round. It is not allowed to send the value V and the value U to P and Q respectively. So the sigma allows us to define this this property relatively simply. So we define it formally as so. For any triplet of processes P, R, and R prime, and any process sequence W, if P or whatever P sends to R regarding the process sequence W, P must also send to R prime regarding W. Given this formal definition, we want to examine how easy it is to solve synchronous agreement problems, for instance, that of broadcast agreement. Recall that broadcast agreement is the problem where we have a single source process and then every other non-faulty process must agree on that process's input value. Turns out that given strong non-equivocation, this is quite simple. So it looks like this. We simply return the value that was, or whatever message or not message was sent in the first round. And because of the strong non-equivocation property, we know that every non-faulty process will have the same value stored for that sigma entry, for that process sequence. If you think a little bit about it, it's not very surprising. Strong non-equivocation essentially models a broadcast channel. And we've now shown that we can easily achieve broadcast agreement given this property. But that's not surprising, as it was a model of a broadcast channel, right? Things become much more interesting when we look at weak non-equivocation. So weak non-equivocation is supposed to encompass the idea that equivocation is prevented by ensuring that every process that receives a message receives the same message. Or in other words, each round a faulty process can choose to send a message or not per recipient. All messages sent must be the same message. So this model fits with a trusted cryptographic component where the process can choose a value to store for each message and then attest that they have stored that value, but they cannot fake the attestations. Also, they can choose whom to send the values and attestations to. As with the strong non-equivocation models, the processes are allowed to lie, but we now also allow the processes to omit any and all messages. What we do not allow faulty processes to do is equivocate. That is, sending different values where we're supposed to send the same value, or for the same round, sending two different values. Yes. Formally, we can define this in terms of sigma as follows for any triplet of processes P, R, and R prime, and for any for all process sequences W. If P sends a message to R regarding W, and P sends a message regarding W to R prime, then P has sent the same message to R and R prime regarding W. So, given this formal definition of weak non-equivocation, how easy is it to solve broadcast agreement? Well, turns out it's a little bit more difficult under weak non-equivocation than strong non-equivocation. This here is the algorithm by Pierce, Shostak, and Lampert, which we have adapted slightly to handle the better fault tolerance of weak non-equivocation. The adaptations are essentially represented in these two places. You don't have to understand the algorithm. I would much rather give you an intuition as to why it works with this lower fault tolerance. And the intuition is comes really from the classical problem of Byzantine generals, where we have a single process that is a general and two lieutenants, and we have to achieve agreement in this setting. So under weak non-equivocation, what can a faulty source process do, or a faulty general then do? Well, it can act non-faulty, in which case everything's good, everybody agrees on the value. Then the general can choose to send no messages to his lieutenant. In this case, both lieutenants will know that the general is faulty since the general omitted a message, and so they know they can trust the other lieutenant when they report that they did not receive a message either. In this case, the two lieutenants can simply choose a default value, and we have achieved agreement. Then the last case is that the general can report a value to only one of its lieutenants. In this case, the other lieutenant will know that general is faulty, and will then know that they can trust whatever the other lieutenant forwards in the next round, because there's at most one faulty process. So in any of these cases, we can achieve agreement. And in the classical problematic scenario of business generals, namely that where the process equivocates, that is sent two different values in the first round, that cannot happen under weak non-equivocation. It's simply this is what is prevented by the weak non-equivocation property, and so we can achieve agreement for any case of a faulty general, and that I hope gives you an intuition as to why the fault tolerance is lower given weak non-equivocation. So we have now examined the different fault tolerance of agreement under the different notions of non-equivocation, and I want to compare the two different notions of weak non-equivocations with solutions to other known agreement problems. I also want to compare them to other fault models. Then the picture here is a reference to the crusader agreement problem, which you'll see in just a minute. So we saw earlier that strong non-equivocation gives a trivial solution to broadcast agreement. Similarly, if we assume a broadcast agreement oracle, we can easily achieve a sigma with a strong non-equivocation property, namely simply by using the broadcast agreement oracle for each message sent in the sigma. This is relatively obvious. Strong non-equivocation is in some sense models a broadcast channel, as I mentioned earlier. It's much more interesting that the same argument can be applied to the notion of weak non-equivocation and the problem of crusader agreement. Crusader agreement is a problem similar to broadcast agreement, but instead of the non-faulty processes agreeing on the value when the algorithm is done, then the non-faulty processes either agree on the value or they know that the source is faulty. So if they know the source is faulty, they do not have to agree on a value. This is exactly the case for any message sent under weak non-equivocation. So if I receive a value under weak non-equivocation, I know that everyone that received a value received the same value. If I do not receive a value in a certain round from a certain process, I know that that process is faulty. This indicates that any algorithm that uses a crusader agreement oracle could just as well use a weak non-equivocation primitive, and vice versa, at least under this system model, that is a synchronous reliable system model. So we modeled the non-equivocation properties as fault models, which allows for very clean analysis of the fault tolerances and other properties. one other consequence is that they, of course, will have a relationship with other fault models. And one of the more interesting relationships is that between the authenticated Byzantine fault model and weak non-equivocation fault model. So at first glance, the authenticated Byzantine fault model may look to be strictly stronger than weak non-equivocation. So both of them are weaker than omission and stronger than the Byzantine fault model. And the authenticated Byzantine fault model has a lower fault tolerance for broadcast and interact consistency. That's what you can see here in this table. Authenticated Byzantine has n greater than t fault tolerance for broadcast agreement and interact consistency, while weak non-equivocation has a fault tolerance bound of n greater than 2t for both of these problems. However, it turns out that weak non-equivocation has runs that are not encompassed by the authenticated Byzantine fault model and vice versa. Namely, if a faulty process equivocates, but no process lies about the value of a non-faulty process, then the run is encompassed under the authenticated Byzantine fault model. On the other hand, it's not encompassed by the weak non-equivocation fault model because a process equivocates. On the other hand, if we have a faulty process that lies about the value of a non-faulty process, but no process ever equivocates, then the run would be encompassed by the weak non-equivocation fault model and not the authenticated fault model. So they are in some sense overlapping, but they also each have a space of runs that are not encompassed by the other. So in summary, the paper's central point is that we have noticed a discrepancy with the uses of the term non-equivocation literature. We've used this discrepancy to define two different notions of non-equivocation as fault models, and then we've examined their properties with regard to synchronous agreement problems. Most notably, we have examined their fault tolerance bounds, which have led to these fault tolerance bounds. Yes. Thank you so much for watching. I hope you enjoyed. Bye.